In this video, I'm going to show you how to compute indefinite integrals of algebraic functions using a change of variable, also known as u-substitution. So here we've got an integral. We want to compute integral of 2x times the quantity x squared plus 3 to the 5th power. Now one option, of course, would be to multiply out this binomial to the 5th power, but that would take some time. So is there a faster way to compute this integral without multiplying out that binomial? Yes, in fact, there is. We can perform a change of variables. And what that entails is defining a new variable u. Let's just put it over here. We don't know what we're going to set u equal to yet, but we're going to have to choose some expression of x for u so that when we substitute u for x in this integral, the integral becomes entirely in terms of u and easier to solve. Now the key to choosing u is to look for an expression inside the integral whose derivative also appears inside the integral. And ideally this expression that u takes on should be as large as possible so as to simplify the integral as much as possible. So looking at this integral here, 2x times the quantity x squared plus 3 to the 5th, the hard part about this integral is the x squared plus 3, the quantity to the 5th power. That's what's making the integral hard. So let's see if there is a derivative somewhere. If we were to take u equals x squared plus 3, then does the derivative of that appear also? Well, derivative of that is just 2x, and hey, that appears over there. So why don't we do that? Let's take u equals x squared plus 3. And if we make that substitution, then we have du over dx is equal to the derivative, which is just 2x. So du equals 2x dx, and indeed that's the rest of the integral, 2x dx. So let's get ready to substitute in our integral. First, let's just rearrange it to make it very clear what's being substituted. So we've got this quantity raised to the 5th power. That quantity is x squared plus 3. And then we've also got a 2x dx. So this x squared plus 3, that's going to be u, that's our u variable here, and then our 2x dx, that's just going to be du. That's what du is equal to. Alright, so writing our integral, again we have integral of u to the 5th, then times du. And that's a lot easier to solve. Now this is just a simple power rule integral. We just increase that exponent by 1, so u to the 6th, and then divide by 6, so 1/6 u to the 6th plus our constant. But we want our final answer in terms of x, not u, so we can just substitute in what we said that u was. U is just x squared plus 3, so let's put that in. 1/6 times x squared plus 3, the quantity raised to the 6th power, plus our constant of integration, and there we go. There is our integral. And again, to highlight the utility of this method, this was to the 5th power, which would have been tough to multiply out, but we didn't have to multiply it out due to the u-substitution. We totally bypassed the need to multiply it out. If this 5th power were like the 100th power or the 1000th power, it would still be just as easy since we didn't have to multiply out at all. Alright, here's another problem. So now we want to compute the integral of x squared over the quantity x cubed plus 1 squared. Again, this is a pretty tough integral as is. This is a rational function, and rational functions are notoriously hard to integrate as is, but we can make a u substitution to make this problem easier. So what is u going to be equal to? Well, again, we're looking for an expression of x that would be simplified by lumping it into a single variable and also whose derivative appears in the integral. And what jumps out at us initially is this denominator here, x cubed plus 1. That looks like it could be simplified by lumping it up into a single variable. And does its derivative occur in the integral? Well, derivative of x cubed plus 1 is just 3x squared, and we've got an x squared in the integral, so we're only off by a scalar factor, and we'll be able to make a minor adjustment to take care of that, as you'll see. So let's just set u equal to this denominator here, this expression inside the squared in the denominator, u equals x cubed plus 1. That way du dx is equal to 3x squared, which means du equals 3x squared dx. And we've got an x squared dx over here, so we'll be able to make this work, as you'll see. So why don't we just rewrite the integral now? So integral of, let's take care of this bottom first. So 1 over that quantity squared. The quantity is x cubed plus 1. And then we've got our x squared dx. But before we write our x squared dx, we want to introduce a 3x squared in there. So why don't we first multiply by a third? That way we can multiply again by 3x squared dx, and the 3's will cancel out, leaving this integral the same as we originally did, but now we see exactly where the du comes in. The du is right here, that's du, and then the u just takes the denominator here inside of the square, that's just u. So we can write this again. This is just 1 over u squared, and then times a third, and then times du. Now this is a lot simpler. It just contains u, and it's a simple integral, so why don't we go ahead and integrate? We'll just pull out that 1/3. So 1/3 times the integral, and we've got 1 over u squared. Why don't we write that as u to the -2, so that way you can apply the power rule, and then a du at the end. So go ahead and integrate that, 1/3, and then u to the -2, well, you just add 1, and then applying the power rule to u to the -2, just add 1 to the exponent. So u to the -1, -2 plus 1 is -1, and then divide by that exponent over -1. Okay, and then plus our constant of integration. Let's just go ahead and simplify that. So this becomes 1/3 times over -1 just means a negative, so negative, and then u to the -1 is just 1 over u, all right, and then plus our constant, and that just becomes 1 over, well, there's a negative 1 over 3u plus our constant, and let's go ahead and bring that up here, substitute back in for u to get our answer in terms of x. That's just -1 over 3 times u is just x cubed plus 1, and then plus our constant. And then we're done. That's the integral. All right, here's a final example. We want to compute the integral of x times the square root of 2x minus 1 dx. Again, we want to do a u-substitution for the complicated part of the integral. What is making this integral tricky? Well, it's the 2x minus 1 inside of the root. That's what's making this integral hard. So why don't we let that be u. U equals 2x minus 1, and don't worry about finding the derivative in the integral just yet. We'll address that soon, but you'll see that because the derivative of u here is constant, this will turn out nicely. Alright, so let's just work with this substitution here. We'll take the derivative, see du dx equals 2, so that means du equals 2 dx. And this time, instead of trying to sub in for du here, let's solve for dx and then sub for that in terms of du. So just multiply both sides by half, get a half du is equal to dx. Now let's write this integral again, substituting in this information. Integral of x times the root of u, u is just 2x minus 1, and then times dx, and this time dx we're going to write as 1/2 du over here. So times a half du. Now there's a problem with this integral still. We still have an x in front of everything, and we want our entire integral to be expressed in terms of u. So what do we do about that x there? Well, we can express x in terms of u. We have an equation, u equals an expression of x, so let's just work backwards to figure out what x is in terms of u. So maybe add 1 to both sides, u plus 1 equals 2x, and then just divide both sides by 2, u plus 1 over 2 equals x. And now this is what we're going to substitute in for that x over there. So this will just be the integral of u plus 1 over 2 times the square root of u, then times a half du. And this is great because now our integral is all in terms of u. There's no x's in there anymore. Moreover, we no longer have a complicated expression inside of a square root. It's just u now, and that can be written as just u to the power of a half, which means we should be able to simplify this to just some powers of u, which are easy to integrate. So let's go ahead and simplify this integral now. So let's move the halves out. A half times a half is a fourth. So let's move that out of the integral. So a fourth integral of u plus 1. And let's write that root u as u to the power of the half, u to the half, and then times du. All right, so now let's go ahead and distribute this and we'll get some powers of u. So 1/4 integral, u times u to the half is just u to the 1 plus a half, or just u to the 3 halves, and then plus 1 times u to the half, so just plus u to the half, all that du. Now we can just solve this integral using the power rule. So a fourth on the outside, then u to the 3 halves, just increase the power by 1, so u to the 5 halves, and then multiply by the reciprocal of that to cancel it out, so 2/5 u to the 5 halves, and then the second term, again increase the power by 1, so u to the half goes to u to the 3 halves, and then multiply by the reciprocal, so times 2/3, and then lastly add our constant of integration. Now let's go ahead and simplify this. We'll just multiply the 1/4. 1/4 times 2/5 is just 2/20, which is just 1/10, u to the 5 halves, and then 1/4 times 2/3 is 2/12, which is just 1/6. So 1/6 u to the 3 halves, then plus c. And our last step, of course, is to write this all in terms of x. So we'll bring that up here, and then sub in what we had for u. U is just 2x minus 1, so this becomes 1/10 times 2x minus 1 to the 5 halves, and then plus 1/6 times 2x minus 1 to the 3 halves, plus our constant of integration, and here we go. There is the result of the integral. Okay, so recapping this example, this was a bit different than the previous ones, but it illustrates the main lesson learned from u-substitution. The main lesson is that u-substitution is useful if you ever want to condense part of your integral into a single term, like this 2x minus 1 inside of the root here. And so the only thing that you have to do to make that work is you have to make sure that you can express the rest of the integral in terms of u as well. And you've got several options when it comes to how to do that. You might solve for what du is in terms of dx and then just lump part of the integral into du, or you might solve for dx in terms of du and just sub it right in. You might need to get rid of some other terms in your integral by back solving for what x is in terms of u. However it works out, you just need to get your entire integral in terms of u, and then since you've simplified a part that was initially kind of rough, then the integral should be a lot easier to compute. Great, so now we know how to solve complicated indefinite integrals using u-substitution. And in the future, we'll also see how to apply u-substitution to definite integrals as well.